All right, guys, welcome back. I hope you enjoyed your little bit of Easter and spring break there. We are going to go ahead and jump right back into another lesson via our virtual instruction. We're going to pick up where we left off, talking about systems of equations. So, prior to the break, we focused on nonlinear systems of equations, or sorry, linear systems of equations. Two or more lines that were going to intersect in a common location gave them a solution. So we first worked with linear systems that had two variables, so just an x and a y in an equation. And then we looked at linear systems that had three variables, so an x, a y, and a z in the equation, finding solutions for those both algebraically and graphically. We're going to continue on that topic of systems of equations, but now we're going to look at things including equations that we have talked about this year or in past classes other than lines. So this is target SE3, which is nonlinear systems of equations. So you will find the notes packet online in your Google Classroom. If you can print the notes out, go ahead and do so, and then you can fill out the packet to follow along, pausing the video as needed. If you don't have the access to a printer, that's okay. Just follow along and take notes on a sheet of notebook paper. Remember, currently as we are assessing online as well, each assessment will be open notes. So you want to make sure that you take good notes, as you guys will have these at your resource as a resource to help you when it comes time to solving problems. So without any further ado, let's go ahead and get into what we're focusing on here with nonlinear systems of equations. So we want to basically find solutions to nonlinear systems. So just as a quick review, we had basically with linear systems, we had some three cases. We either had lines that would intersect in one place and they would have one solution, or lines that would not intersect. They would be parallel, and they would have no solutions. Or we'd have lines that overlap one another. Essentially, they're the same line, and they would have all solutions. When we talk about nonlinear systems of equations, we're going to have a variety of possible solutions here. The same concept is going to be held true. So let's take a look at this first example I put up. The solution to this system would be whatever point is located right here where they intersect. That would be the given solution to the system. Same concept is going to hold true even if we start working with nonlinear systems. So let's go ahead and take a look at these two graphs. In both of these graphs, we see, in this examples, we see a line and another shape. Two shapes we should be familiar with. So the graph on the left is a parabola, and we've been working with parabolas very frequently this year. The graph to the right, we have a line and a circle. You probably worked with circles a lot in geometry. We haven't seen them a lot here in Algebra 2, but we're going to start seeing a little bit more of them with this unit. In both of these cases, if we take a look at the graphs, we may notice that over here on the left, the parabola does not intersect the line. And remember that lines continue endlessly, and parabolas also continue endlessly, but judging by the arrows and the direction at which this line and this parabola is going to continue, these are never going to intersect. The same thing with the circle over here and the line in the example to the right. So the line will continue endlessly. The circle will just be this given shape here, but still they will not intersect. So as we take a look at this example here, we would say that there is no solution to these two systems of equations. So whatever equation is representing this parabola, and we could figure it out, but we don't need to, but the equation for this parabola and the equation for this line would not have a solution. Same thing with this circle and that line, there would be no solution. So one of the first options we're going to have is there is no solution to the system of equations. Now with lines, if there was a solution, there was only one. And we can see that examples here. So again, I have a parabola and a line on the example to the left, and a circle and a line on the example to the right. In each of these cases, the curve intersects the line in exactly one location. So here we have that intersection on the left, and over here we have that intersection on the right. So each of these would have one solution. Now as you go into more in-depth mathematics, you'll eventually find out that these lines are tangents to the curve because they intersect in just one location. But for right now, just being able to identify that there's one intersection tells us that there's one solution. Now if we wanted to find this intersection, what we would need to do is basically find the coordinates for that point. So if I look at the example here on the right, it moves 2 units to the right on the x-axis and 3 units down on the y-axis. And so our solution could be 2, negative 3. We could also write that solution as x equals 2, y equals negative 3. In the example on the right, they have those coordinates listed for us. So that coordinate would be 1, 2. It moves 1 to the right on the x-axis and up 2. So our solution could be the coordinate pair 1, 2. And we could also write this as a solution where x equals 1 and y equals 2. So in both of these cases, we see an example of one solution. Now, where nonlinear systems differ from linear systems is when we have solutions, there can be more than one solution. It doesn't have to be no solution, one solution, or all solutions. So take a look at these two examples. Again, we're dealing with a parabola and a line on the left, and a circle and a line on the right. In each of these two examples, we may look at the graphs and notice that they intersect in two locations. So in both of these cases, there are going to be two solutions. And again, we could list those solutions by finding the coordinates for the points, which it's given here to this example on the right. And the example on the left, they're going to be decimal approximations, but still, the coordinates would give us two separate solutions. So when we see nonlinear systems, sometimes they'll intersect in more than one location because we're dealing with some curves here, a parabola and then a circle, intersecting lines, and so we have two solutions in this case. Now let's take a look at some more examples. And let's take away the line. Now let's compare a circle to a parabola. So we can use nonlinear systems of equations. The first examples did include a line and then a curve. In these two examples, there's no line whatsoever. Both of these are curves. So if we take a look at the example on the left and on the right, they're both circles and parabolas. And if I take a look at this parabola here, I may notice that it intersects in three locations. So this example right here has three solutions. So there are 3 points of intersection between the parabola and the circle, so there are 3 solutions. If we take a look at the example on the right and count the intersections, we see that there are a total of 4 solutions. So the number of solutions is dictated by what type of equations that we are combining into the system. No longer are we just looking for a single solution. We may be looking for multiple solutions. And you may ask yourself, well, how many? Well, the answer is really infinitely many. So I made this graph on Desmos. It's not the best looking graph, but you can get a good idea. Here's the x and y axis. I have a cubic equation represented by this curve, and then a circle. Now, if we look at the number of intersections here, 1, 2, 3, 4, 5, 6, we see that there are 6 solutions here. So depending on the curves that we're representing, we may be dealing with a very high number of possible solutions for our system of equations. So the first thing that we want to do probably if we're unfamiliar with what type of graphs we're looking for is take a look at the graph and identify how many solutions we're looking for. Which takes us to problem number 1. So problem number 1 in the notes packet says determine the number of solutions for the below system of equations. So what I'm looking at here, if I take a look at the system of equations, we see that this top equation is a circle. And then this bottom equation is going to be a line. So they fit the circle and line forms. We could rewrite this in y equals mx plus b form if we wanted to. We will eventually. But this is going to be a circle on top, and this is going to be a line. So circles and lines, we could have a circle, for example here. We could have a line that intersects 0 times, so there could be no solution. We could have a line that intersects twice, so maybe 2 solutions is the answer that we're looking for. We're looking for 2 total solutions. Or we could have a tangent line that intersects once, and there we might be looking for 1 solution. So we're unsure. We know that a circle and a line can intersect 0, 1, or 2 times. So we know that the number of solutions is either going to be 0, 1, or 2. To figure out how many, we need to take a look at the graph. So if you have Desmos at your disposal, it's pretty quick to type these in. So you can type in the format of the equation exactly as they are written. So I think that was x squared plus y squared equals 25. And then x minus 1, or sorry, x minus y equals 1. And we can see that there's going to be two solutions. Now, Desmos is not always going to be available to you. So if you have a graphing calculator, you can still take a look at the graphs here and come up with the same answer, that there's going to be two solutions here. On the graphing calculator, if we hit the y equals button, that is our graphing options, and so everything has to be set equal to y. So what I'm going to do is I'm going to go ahead and rewrite these two equations to be set equal to y. So like before, I'm going to letter the equations a and b just to organize my work. So equation A is x squared plus y squared equals 25. So if I want to get y by itself, I may notice here that I want to subtract x squared from both sides. So it's going to cancel out on the left side. On the right side, we're just going to be left with 25 minus x squared. Now, I kind of have y by itself, but I need to get rid of this square. So what am I going to do to get rid of the square? If you said to square root both sides, you would be correct. So on the left side, the square and the square root cancel each other out. On the right side, we would have the square root of 25 minus x squared. Now, don't forget, when you're solving or rewriting an equation, we need to have both plus or minus options within taking a square root. So we're looking for possible solutions here for that equation. So some of them could be negative values for x, some of them could be positive values, or sorry, inside the square root, some could be a positive value or a negative value from this expression. So when we put this equation into the calculator, we need to make sure that we put both the positive and the negative. So let me show you first what happens if I only put in the square root of this expression, and I forgot to, let me make sure I type it in correctly. But let's say I forgot to put the plus or minus. When I take a look at the graph, and I'm going to hit zoom 6 to make sure I'm in the standard window, you see kind of this half oval shape here. We know that A should be a circle, so I have to make sure that I also have the negative portion of this as well. And now I can see the bottom. Now, because this looks like an oval in probably most of your calculators, if we want to make that a little bit more square to see a circle, you can hit zoom, and then you can come down here to this fifth option, zoom square, and that's going to just adjust your window so that it's going to be a square window instead of the rectangular shape that you see here. So now we can see the circle. Now there is a little bit of a gap there probably in your calculators just because of the sum of the mathematics that go into finding out this expression. So when we work with algebraic expressions, we're going to have to account for that gap. So this circle, remember that this circle should close here. So there's my expression for A put into the calculator. B is much easier to rewrite. So x minus y equals 1. I'm going to go ahead and subtract x on both sides. So that would be 1 minus x. And now I do have a negative y. So I need to divide by negative 1, which would essentially change the sign of everything. And you can reorder that if you want to, but it's not necessarily needed. You don't have to. And then I can type in the equation now, negative 1 plus x into my graphing calculator. So remember the first two spots in this equation are just a, because there's both plus or minus in front of the square root. Then this third spot is b, and now I can graph, and I can see that there are two solutions here. So if you have Desmos, you can type in any equation the way that it's written, and you're going to see that picture on Desmos. And you can look for the number of intersections and find those intersections. Desmos is a good option for you. But if we don't have that, if you're working on standardized testing, you definitely can't use a computer, so you would need to use your graphing calculator. And so we'd have to rewrite those equations into a y equals form, and then putting in the graphing calculator and see that there are two solutions. So this is how we can find the number of solutions. Now, to find the exact solutions, we could do it two ways. We can find the location where they intersect graphically. So Desmos is awesome for this because I can just go click on the points where they cross, and there's my two solutions for this system. We can also do that on the graphing calculator by hitting second, trace, and intersect, and then finding the intersection points. And we'll come back to that. Sorry, I did this incorrectly, but we'll come back to a little bit more detail on how to find those intersections. The other thing that we can do is solve systems algebraically. So what we're going to do in these notes, we've done a lot of solving systems graphically. We should be good at that pretty quick and easy. The calculator's not going to make mistakes as long as we input it correctly. What we want to focus on mainly here is algebraically solving these systems. There's two ways that we could do this. We can use the elimination method and we can use the substitution method. I prefer the substitution method because the elimination method works in some very rare cases. Usually it's not going to work for us. So we're going to go through all of these using substitution. If you know how to do elimination, or if you watch one of the additional resources videos that explains how to do elimination and you like that method, you understand it, go ahead. But I'm going to simplify things and just use substitution here. So basically what I want to do to solve these algebraically, and then we're going to check with the graphing utility, is get both equations set equal to y. So the first equation is already set to y. Y equals x squared minus 2x minus 3. That one's good. The second equation, I'm going to need to do a little work to get y by itself. So I'm going to subtract 2x from both sides. So I'm going to leave this first equation just written the way that it is. The second equation, I'm going to go ahead and subtract 2x from both sides. So that's going to give me a negative y equals 7 minus 2x. Remember, we can't combine variables with constants, so it's just 7 minus 2x. I do need this y to be positive, so I'm going to divide by negative 1, which essentially changes the sign for everything. So this would be y equals negative 7 plus 2x. Now, if I have both equations set equal to y, it's a quick substitution. So we know what y equals here on the left. It's x squared minus 2x minus 3. And we know what y equals on the right. It's negative 7 plus 2x. So these two things have to equal one another. Basically, what I'm doing here is I'm taking this expression for y and substituting it in there. And now I can use an algebraic method to solve this equation. Sorry, I wrote that down wrong. Negative 7 plus 2x on the right side of the equation. But now we can use an algebraic method to solve this equation. So this is a quadratic equation. We want to get this equation set equal to 0. So I'm going to add 7 to both sides. So if I add 7 to both sides, it's going to give me a positive 4 here on the left and then a 0 on the right. I'm going to subtract 2x from both sides. So that's going to give me a negative 4x on the left and a 0 on the right, which is good. Now I have x squared minus 4x plus 4 equals 0. So what I can do now is I can simplify this equation on the left side. It does factor, so I can factor this down into x minus 2 and x minus 2. So x minus 2 quantity squared would equal 0. So negative 2 squared is 4, and negative 2 plus negative 2 is negative 4. So x minus 2 quantity squared equals 0. If I want to solve this, I can square root both sides. The square root of a square is just the expression inside the square, so the square and square root cancel out. I would square root 0, but the square root of 0 is just 0. So now I can add 2 to both sides and get that x equals 2. Now remember, we are solving for both x and y, so part of my solution is that x equals 2. The other part of my solution is y. Well, now I can figure out y by just taking this 2 and substituting that back in. So then this expression would be y equals negative 7 plus 2 times 2. If I want to type that into my calculator real quick, or if you can do that in mentally, that's okay. Y equals negative 7 plus 2 times 2. And that answer would be negative 3, so y equals negative 3. So we could represent this as the solution of x and y. We could also represent this as coordinate pair 2, negative 3. Either way would be an okay way to represent the solution. Now, it does say to check your answer with a graphing utility. So basically, if we have this written, let me go back to the top and I'm going to circle two pieces. If we have this written so that our equations are equal to y, and that's why I mainly use substitution, now I can just type this into my graphing calculator and find those intersections to make sure that my solution that I got here is correct. So notice that we only had one solution. A solution is a coordinate pair, so though I had a value for x, and a value for y, that gives us one solution because that value for x goes with that value for y. So I'm going to go ahead and type in the two expressions, y equals x squared minus 2x, 2x minus 3, and y equals a negative 7 plus 2x. And if you wrote that in different order, that's fine. Now I'm going to go ahead and hit zoom 6 just to see the graph on the standard window. And I can see there that it looks like it intersects just once. I want to double check. So if you want to double check, you can hit the zoom key and zoom in here. I'm going to move my cursor over a little bit. You don't necessarily have to do this, but I'm going to move my cursor over there where it looks like it's intersecting, and then I'm going to zoom in. And as I zoom in, it still looks like it's intersecting just one time. So we could find that intersection on the graphing calculator. So to find the intersection on the graphing calculator, hit second, trace, intersect, fifth option. Now your calculator will say first curve, and you'll have a blinking cursor on it. Make sure that cursor is on one of the two equations. So right now it's set up on the parabola. Now I'm going to hit enter. It'll say second curve. I want to make sure it's on the line because their second equation was a line. Hit enter, and then when it says guess, you don't have to worry about guessing, and then it's going to find that point for us where they intersect. Took us a little bit. Now, one thing that we might notice here is that these numbers are rounded a little bit. Depending on where you set your locations for the finder, the intersection finder on your calculator, it might round your answer slightly. So this answer should actually read exactly -3 and exactly 2. So we did find this value correctly. So we want to make sure we use that graphing utility depending on what model you have and what method you use as a check, but also making sure we use the algebraic method to know the exact answer there. So the solution in A is 2, -3. So in the first case, we found a parabola and a line and found their single intersection point, and that was the single solution. Here in this second case, in B, we have another parabola. I noticed that because there's an x squared. This is a circle down here on the bottom. An x squared plus a y squared is going to give us a circle. So I have a parabola and a circle. So remember back to the examples for possible solutions. I'm just going to draw some sketches here. So I could have no solutions. You don't have to draw this if you don't want to. I could have one solution where the parabola just touches the circle. Could have two solutions where the parabola passes through the circle. I could have three solutions where it passes through, but the vertex of the parabola is also on the circle. And I could also have four solutions where it passes through the circle in two different locations on each side of the axis of symmetry of the parabola. So we don't know exactly how many solutions that we're looking for. If you wanted to graph this from the start and find the number of solutions, you could go ahead and do this. We're going to go through the algebraic method to take a look at and see if we can find those solutions algebraically, and then we're going to graph afterwards. Again, we're going to use the substitution method here. So in order to use the substitution method, we want to make sure that each equation is equal to y. So here with this first equation, you could letter A if you wanted to, but this first equation right on top, to get y by itself, it's just an addition. So all I need to do is add 1/2 x squared, add this component to both sides. So that what that would leave me with is y equals -3 plus 1/2 x squared. And you can reorder that if you would like to. On the second equation down here on the bottom, I need to subtract this x squared to both sides. So that gives me y squared equals 41 minus x squared. Now, the second equation isn't quite finished yet. We don't have y completely by itself. So I need to get rid of this square value here. And in order to do that, I would square root both sides of the equation. So the square and the square root would just cancel each other out, so I'm left with y. Remember, when in the solving process, when creating a square root, you have to have plus or minus. So 41 minus x squared is now under the square root. So now that I have both equations equal to y, I can substitute. So -3 plus 1/2 x squared equals plus or minus the square root of 41 minus x squared. Now we want to solve this algebraically. So, how do you get rid of a square root? In order to get rid of a square root, and to solve this, I need to square both sides. So I'm going to square with the square root, and I'm going to square on the other side. So the square and the square root, I'm going to work with the right side first. The square and the square root cancel each other out. Now, technically, would be a plus or minus inside the parentheses, and then squared. So it doesn't matter whether it's plus or minus. It's just going to both a positive and a negative when you square them are positive. So that gets rid of our square root. So the right side of the equation, now we have gotten rid of the square root. Remember when we square something on the other side, you do square both terms. So let me square this first term, negative 3. So negative 3 squared is 9. And then let me square this second term, 1/2 x squared. Remember, we'd be squaring the 1/2, which is 1/4. And you can do that in your calculator if you want to. Let me show you that real quick. So if I did, oops, clear that out. If I did 1/2 squared, it'd be 0.25, which I could do as a fraction, is 1/4. X squared, the 2 and the 2 would multiply, would be x to the 4th. Now also, remember that when you square binomials, essentially what we'd have is distribution here. So also what we would get is this negative 3 being multiplied to 1/2 twice and then added together. So what we need to do there is take, let me get rid of some of that, clean that up. What we basically need to do there is take this first term, negative 3, times this middle term, 1/2 x squared. And so I'm just going to multiply it by the 1/2 and then double that. So what I'd get here is a negative 3x squared. So that's one of our shortcuts there that we've been dealing with this year when squaring a binomial. You could always multiply this out if you wanted to, write it as two binomials and distribute like I kind of had there on the screen. So the left side simplifies to 9 minus 3x squared plus 1/4 x to the 4th power. So this looks kind of confusing maybe, but it is a polynomial. And remember when we solve, we want all polynomials set equal to 0. So what I'm going to do here is add x squared to both sides. Add x squared and add x squared. And then I'm going to subtract 41 from both sides. And I'm going to reorder these terms. So I'm going to write the 1/4 x to the 4th, and then negative 3x squared plus x squared would be negative 2x squared, and then this 9 minus 41 would be minus 32, equal to 0. Now, we can solve this polynomial. It looks kind of complicated, mostly because we have a fraction here. So let's multiply everything here by 4. You don't necessarily have to do this. If you can work with the fraction, go ahead. But if we multiply everything here by 4, that gets rid of the fraction. So x to the 4th minus 8x squared minus 132 equals 0. So I just multiplied everything by 4. 32 times 4 is 132. Oh, mistake. Not 132. About 128. So let me double check that number. 32 times 4 is 128. Okay, good. So now what we can do here is we can factor this. So remember, x to the 4th factors like an x squared does. It just breaks apart into x squared and x squared instead of x and x. We know that we have a plus and a minus here. So a positive value and a negative value, because it has to multiply together to give us a negative 128. Now, factors of 128 that would add together to give you negative 8. The easy way to find this on the calculator is 128 divided by x, and then go look at your table. So we want two numbers that are separated by 8 values, and that would be 8 and 16. So this would have to be a positive 8 and a negative 16. Now, we can set both of these equal to 0. X squared plus 8 equals 0, and x squared minus 16 equals 0. So I'm going to first start with the x squared plus 8 and subtract 8 from both sides. So x squared equals negative 8. Then we would square root. So x equals plus or minus the square root of negative 8. Now, remember earlier in this year, we talked about how to simplify this. We wanted to simplify with imaginary numbers. But we're looking for points on a graph. Imaginary numbers are not going to show up on a graph. So anytime you get an imaginary number, you can essentially get rid of that answer because that's not going to be a solution that's going to be a valid solution for our equation because it's not going to show up as an intersection on the graph. So over here to the right, x squared plus 8 gives us an imaginary unit, so no solution there. Then on the right, I'm going to add 16 to both sides. X squared equals 16. Then square root, so x equals the square root of 16. So x equals plus or minus 4. So what I'm getting here is two answers for x. X equals positive 4 and x equals negative 4. Now, if I want to figure out what those common values have for y, here's one of my solutions for x, there's my other. I can go back to either of these equations at the top and substitute in x. I'm going to use this one over here on the left because it's not with a square root. So let me go ahead and type in y equals, so negative 3 plus, I'm going to do this all in the calculator, negative 3 plus 1/2 x. My first x was positive 4, so x is positive 4 squared. And that corresponding y is 5. So I'm actually going to go ahead and put these two in the same box because they go together. So when x is positive 4, y is positive 5. We do need to make sure we find those y values. I would do the same thing for y, or x is negative 4. So go back to this equation and type that equation into the calculator. Negative 3 plus 1/2 times negative 4 squared. And if you knew, you might not have to do this because the negative 4 would just become positive, and it's going to give you the same y value. So y equals 5. So this actually has two solutions. The solutions are in coordinate pairs 4, 5, and negative 4, 5. Now, algebraically, this one is a little bit of a bear. It's pretty difficult. So it's not very likely that I'm going to have you guys have to solve one of these on an assessment algebraically. But we should be able to do this graphically. So I'm going to go back again, and I'm going to circle two parts at the beginning. We do want to check these graphically, and we're actually going to circle the expressions where we had y equals. So it's good to keep track of those because now I can use those to check my answer. So I'm going to go back to the y equals table. I'm going to type in the expressions negative 3 plus 1/2 x squared. And then remember with the square root, I'm going to need a positive option. So this is a positive square root, 41 minus x squared. And now this is a negative square root, 41 minus x squared. And I can graph those. I can hit zoom 6 for the standard window, or if it's a circle and I want it to look like a circle, I can hit zoom 5 for square. Hold on. Let me get this back into the standard window first. And I'll just leave it looking like an oval. I know this is a circle because it's a rectangular window, but it looks like an oval. Basically, all we need to do is be able to find the intersections. So here I can see there's two intersections. That's good because we came up with two solutions. Now let me make sure they're the right solutions. Hit second, trace, intersect. It's going to ask you for the first curve. I'm actually going to move my cursor here. Because there's two solutions, I want to find each solution one at a time. So I'm going to move my cursor over here using the left to right arrow keys close to the intersection on the right, and then hit enter. It's going to say second curve, and it jumps me up to the equation at the top, right next to that intersection. That's good. I'm going to hit enter. When it says guess, I'm just going to hit enter. And because I had my cursor there pretty close, it gave me the exact values 4, 5. That matches up with our first solution. Now let's check our second solution. Second trace, intersect. Now it says first curve, and it's over here right next to the solution already found. So I want to use my cursor to move it over to the left. And then hit enter. It says second curve. It's right next to my intersection here. That's good. Hit enter. I'm not going to guess. And there it gives me the solution -4, 5, which matches up with the solutions we found. So we can use the intersection tool to find the solutions. We can also look at the table. So if I go ahead and take a look at the table, and I go over here to the value 4 on x, I can see that the y values are the same for both, sorry, I can see that the y values are the same for y1 and y2, which gives me a solution. If I go ahead and take a look at my x value of -4, I can see that the y values are again the same for y1 and y2, which gives me my second solution. So you can use the table. The table can sometimes be a little bit tricky, so you can use the table as well to make sure that we have solutions there. So the two solutions are 4, 5, and -4, 5. Again, these are probably a little on the tougher side. Sorry I put this question second, but a little bit tougher side algebraically. Not very likely that you guys are going to have to solve one of these algebraically, but graphically, we should be able to rewrite these expressions and put those into the calculator to find the intersections. Let's look at some that are a little bit more friendly to solve algebraically. So again, let's take a look at C. C is similar to our first equation that we had in A, where we have a quadratic equation, a parabola, and we have a linear equation, a line. See if you can find, pause the video here, and see if you can find the solutions algebraically to these two equations. Okay, well, hopefully you got a chance to work there. Let's go ahead and find these algebraic solutions. So C was set up nicely. The two equations are already set equal to y, so we don't have to do any work there. We can go ahead and just substitute right from the beginning. So this top one is y equals, the bottom one's y equal. So we can substitute the two equations, and now we get the expression x squared plus 4x plus 3 equals 2x plus 6. Remember, this is a polynomial, and so we want the polynomial to equal 0 in order to solve. So we get x squared plus 2x minus 3 equals 0. Now, in order to solve this one, we may notice that it does factor to two values, x plus 3 and x minus 1 would be the two values that it factors into. So set them both equal to 0. X plus 3 equals 0. X minus 1 equals 0. You can subtract 3 on the left and add 1 on the right to get your solutions for x. So here we have two solutions for x. Now let's find their corresponding solutions for y. To find their solutions for y, we can just go ahead and substitute back into the equation. So I'm going to do this on the calculator again. So x is -3. I'm going to take that and substitute it into this equation. So 2 times -3 plus 6. So in this instance, y equals 0. So one of my solutions here is -3, 0. Do the same thing with the 1. So 2 times 1 plus 6. And in this instance, y equals 8. So my other solution that I get here is 1, 8. So these are the two solutions. Now, again, let's check this graphically. So this equation in C, again, was set up pretty nicely for us. X squared plus 4x plus 3, we can just type into the calculator because it equals y. And 2x plus 6, we can just type into the calculator because it equals y. We can graph that. And there's my parabola. And there's my line. You can see the two intersections. Hit second trace, use the intersection key. Where it says first curve, I'm going to move it over close to this intersection on the right, hit enter. It's close there on the second line, hit enter. And I'm not going to guess, just hit enter. So there it gives me the first intersection is 1, 8. We have that solution, that's good. Then I'm going to do this again. Second trace intersect. Now I'm going to use the left and right arrow keys to move closer to the other intersection now. Hit enter. On the second curve, it's close there to that second intersection, hit enter, and I'm not going to guess. And there it gives me the other intersection, -3, 0. So we have both of our solutions here found algebraically. So C is one that you are likely to be able to have to solve on an assessment. Let's go ahead and take a look at D. D is also one that you're going to likely be able to solve algebraically on an assessment, but let's go ahead and do this one together. So here we have this is actually going to be a circle there. A lot of us may see that and think parabola because we see the x squared, but if I added the y squared over, it'd be x squared plus y squared equals 16, which is a circle. The bottom one, this is linear because it's x to the first power, so we got a circle and a line. So we could have no solutions, one solution, or two solutions. Let's figure out how many. So in order to do this, we're going to substitute again. Let's try to get y by itself. So looking at this first equation, I'm going to need to move over this 16. So I'm going to subtract 16 from both sides. So I'm going to put the y first. Negative y squared equals x squared minus 16. Now do notice that there is a negative out in front of this y, so I need to divide by the negative one first. So y squared equals negative x squared plus 16. And now I can square root. So y equals plus or minus the square root of negative x squared plus 16. I need to make the other equation equal to y. So first, I'm going to subtract x on both sides. So negative 2y equals 10 minus x. I do need to divide here by this negative 2. So this would give me y equals 10 divided by negative 2 is negative 5. Negative x divided by negative 2 would be a positive 1/2 x, or x over 2. So here's my circle written in y form, and here's my line written in y form. Now, in order to solve this, I'm going to set them equal to one another. So the square root of negative x squared, plus or minus the square root of negative x squared plus 16 equals negative 5 plus 1/2 x. I'm going to star that line because I'm going to come back to that. Now on both sides of this, I need to square both sides of this equation to get rid of the square root. So anytime we need to get rid of the square root, we have to square both sides. So on the left side, the square and the square root cancel out. Remember that plus or minus goes with the square root, so it's gone now. On the right side, I am going to square each term. So negative 5 squared is 25. 1/2 x squared. Remember, I square the 1/2, which you could do in your calculator, but it's 1/4. I square the x, it's x squared. I'm going to have this middle term. So this middle term is by taking these two, multiplying them, and doubling that. So if you need to do this on the calculator, I'm going to do this here so you can actually see what I'm doing. So negative 2 times 1/2. So I'm going to multiply the two coefficients, and then I'm going to double that. So this is going to be negative 5x. Remember, when you square a binomial, there's a middle term, so we have to account for that. So now this is quadratic. There's an x squared. It's a polynomial. We need to make it equal to 0. So I'm going to go ahead and subtract 16 from both sides. I'm going to add x to both sides. So this gives me, I'm going to write the x's first. So 1/4 x plus x is 5/4 of x. You could put that a decimal as you need to, but it's probably going to be easier to write it as 5/4. The negative, 5/4 x squared. The negative 5x, nothing's combined here, so that's just negative 5x. And then 25 minus 16 is 9. It's going to equal 0 because everything on the left side of the equation, which I flipped around, is now the right, canceled out. Here I have this fraction, so I'm going to go ahead and multiply everything by 4 to get rid of the fraction. It's just going to make factoring this a lot easier. So 5 squared minus 20x plus 36 equals 0. Now I need to solve this equation. You could do it a number of ways, but this does factor pretty nicely. So 5x in one and x in the other, because 5x times x is 5x squared. We know both of these factors are going to be negative, a minus and a minus, because it has to multiply together to give us a positive 36. But then when distributing, add together to give us a negative 20. So what we need to do is find numbers here that are going to work. Sorry, let's actually not factor this one. This one's going to be a little bit difficult for us to factor where we're at. So I'm going to take that part away. Let's actually not factor this. Let's use the quadratic formula. We can always use that quadratic formula if we need to. In this case, it's probably going to be easier for us to do the quadratic formula. So remember, quadratic formula, x equals negative b. My b is that second coefficient, so negative b is 20. A negative 20 would make it positive. Plus or minus the square root of b squared, so 20 squared, minus 4 times a, which is 5, times c, which is 36, all over 2 times a, which is 5. So as I simplify this, x equals 20 plus or minus the square root. Now, inside the square root, this would again be 20 squared minus 4 times 5 times 36, which is negative 320, all over 10. Now, we could try to simplify this if we wanted to, but what we see here is that when using the quadratic formula, there is a negative inside of the square root. So earlier in this year, way back in the first quarter, we talked about the discriminant. When the discriminant is a negative number, when it's less than 0, there is no solution to this quadratic equation. And so in this case, the solution would be imaginary. If we're trying to find solutions where it's on a coordinate plane, imaginary numbers, again, don't show up on the coordinate plane. So here we have no solution. Now, it did take us a lot of work to get here, and that's a little bit unfortunate, but algebraically here, we can find that there's no solution because the only values for x would be imaginary numbers, which we could simplify. We're not going to. Now, graphically, we probably could have come to this result a little bit quicker. So if you were forced to solve this algebraically, you have to go through this process, these steps. But if you weren't and you're allowed to do this graphically, I'm going to go back to where y equals. And so y equals a positive and a negative square root of negative x squared minus 6 or plus 16. So we want to make sure we put in both parts of this, the positive square root and the negative square root. And make sure here when you're typing this in that you're very careful. The calculator won't make computational errors, but if we type things in correctly, which I initially did, then the answers are going to be incorrect. So we got to make sure that we're careful how we type things in. So there I have it. I have the plus or minus square root of negative x squared plus 16. So that has to go in 2 lines. Unless you have a super new calculator, you do have, some of you guys do have a plus or minus button there. You can do it in 1, but we can all do it in 2. And then y equals the line, and check out the graph here. So there's the graph of my circle. It's oval because I have this on a rectangular grid. And there's the graph of my line. And so if we look here closely, it kind of looks like they're about to intersect. But if I really zoom in there and take a look at this picture a little bit from a closer perspective, I can see here with that circular curve and that line, there is a little bit of space in between them so they don't intersect, so this is no solution. So our work here checks out. It was a lot of work to get there, but if you have imaginary solutions or a negative square root, anytime you get to a negative square root, that's going to be a solution that's invalid for our systems of equations. So let's go ahead and let's take a look at E and F. Go ahead and pause the video. If you're feeling pretty comfortable about solving these algebraically, go ahead and pause the video and see if you can do both part E and part F. See if you can do both of those, and then play the video and check your answers. If you're not certain you can solve these algebraically, just stick with it, and I'm going to go through these results now. So hopefully you either got a chance to come up with some answers, or if not, let's go ahead and find some answers. So again, in order to solve these, we need y to be by itself. We're going to use substitution. This first one up top, this one's good here. Y is already by itself there up top, so I'm not going to have to do any work with that. In the bottom equation here, I am going to have to move the 3x, so I can do that by subtracting the 3x. So y equals 8 minus 3x. So now I've got 2 equations that are equal to y. I can set them equal to one another. Negative 2x squared plus 6x minus 5 equals 8 minus 3x. This is a polynomial, so I want this to equal 0. I'm going to go ahead and move everything from the right to the left just to make sure my leading coefficient is positive. You don't have to, but it may make factoring a little bit easier for you. And so now I've got 0 equals 13 minus 9x plus 2x squared. So add the 2x squared to both sides, subtract the 6x from both sides, add the 5 to both sides. Now what we need to do is we need to solve this equation to come up with our values for x. This one doesn't look very easy to factor. It's possible, but it doesn't look very easy to factor. So let's go ahead and use the quadratic formula and see what comes up with the quadratic formula. So x equals negative b. My b is negative 9, so positive 9 plus or minus the square root of that b, negative 9 squared, minus 4 times my a value here. I didn't reorder this, so here's a, b, c. If you needed to, x squared does technically come first, and then the negative 9x, and then 13. So my a is the coefficient for x squared. So a is 2, and then c is 13. In this specific problem, it wouldn't matter really, but just in case, just making sure that the a comes in front of the x squared. Now, if I simplify this out in front, it's still just 9 plus or minus the square root of. Now in the calculator, I'm going to go ahead and do the discriminant, what's inside of the parentheses. So negative 9, sorry, let me type that in correctly. Negative 9 squared minus 4 times 2 times 13. And that gives me a negative 23. And right there, I can go ahead and stop. Because what do I notice here about my values for x? Well, my values for x, if I'm going to have a negative inside the square root, means they're going to be imaginary. And if I only have imaginary values for x, there is no solution to this problem. And again, I can check that in the graphing calculator. So I can type in my expressions here. Let me make sure everything else is cleared out. So negative 2x squared plus 6x minus 5. And then I have to use where y equals here, where we rewrote. So 8 minus 3x. Graph. Let me change my window here real quick. You can see it actually decently there, but let me hit zoom and then 6 to get me back to the standard window. And I can see here there's no intersection. So this too is also no solution like that previous one. So if it's easy to factor, go ahead and factor it. If not, go ahead and put it into the quadratic formula, because there's a good chance that if it looks difficult to factor, if it's difficult for you to factor, it can't factor unless you use imaginary numbers, and that for our purposes means that we're having no solution because we're trying to find intersections in a graph, and imaginary numbers don't show up on the graph. In part F, if you went to part F, we have a circle and a line. The circle is x squared plus y squared equals 4, and the line is y equals x, so that diagonal line from quadrant 3 to quadrant 1. X squared plus x squared plus y squared equals 4 is the only equation we need to rewrite in order to substitute. So let me get y by itself. So subtract x squared. And again, this isn't the only method that you can use to solve, but it's just the method we're going to use because it also translates to graphing. Then I'm going to square root both sides, so y equals plus or minus the square root of 4 minus x squared. Now I can essentially set these two equations equal to one another. I can substitute in for y. So this would give me x equals, I'm going to star these again because I'm going to come back and put those in. X equals plus or minus the square root of 4 minus x squared. So now I need to solve for x. So I need to get rid of the square root, which means I need to square both sides of the equation. Well, that's pretty easy on the left side. X squared is just x squared. On the right side, the square root and the square undo each other. Remember, again, the plus or minus is it's basically attached to the square root. So x squared equals 4 minus x squared. And now I can add x squared to both sides. And I get, if I add x squared to both sides, I get 0 equals 4. So, not add x squared. That would be incorrect. Let's subtract x squared from both sides. And I get 0 equals 4 minus 2x squared. Now you could factor this one if you want, but because there's only an x squared and no x term, it's a little bit easier. I'm going to just subtract 4 from both sides. So negative 4 equals negative 2x squared. And I'm going to divide by negative 2. So, sorry, negative 4 divided by negative 2 is positive 2 equals x squared. And now I have to square root both sides. So x equals plus or minus square root x. Sorry, x equals plus or minus square root 2. So we're going to have two solutions here. We're going to have a positive square root 2, and we're going to have a negative square root 2. In order to find those answers, I can go back and substitute into this equation. So notice here that the bottom equation is probably the easier one to substitute in. So y equals x. So if x is positive square root 2, y is positive square root 2. If x is negative square root 2, y is negative square root 2. So these are the two solutions that we get here. Now we do want to make sure that we check this graphically. So if I go ahead and I check this graphically, let's use the two equations. We did rewrite one equation, so y equals x is my first equation. And then my second equation, again, it's a positive and a negative square root. So square root of 4 minus x squared, and negative square root 4 minus x squared. Graph that. There's my line y equals x. There's my graph. I see there are two intersections, so I'm going to find them. Second, trace, intersect. This is where the table is not going to work. So I'm going to use second trace, hit the intersect key. I'm going to move my cursor over close to one of the intersections. Let's choose the one on the right. Hit enter. It's going to say second curve. It's close to that intersection. Hit enter. It's going to say guess and hit enter. Now notice here that there's a decimal. That decimal is 1.414236. And it's both for x and y, so that's good. We know that x and y are the same value. Now let's double check and hit the square root 2, and we can evaluate that in the calculator. And that's that number that we saw, 1.4142136 if you round it. So this, on the calculator, it said a decimal, but that is positive square root 2 and positive square root 2. That's the answer that we gave. Let's check the other one. So second, trace, intersect. Now I'm going to move my cursor using the left arrow key down over here to the other intersection, closer to the left side of the screen. Hit enter. So what we see here is it jumped up top to this intersection, or to this curve. And if I move left or right, it actually ends up disappearing. So there's actually three curves on this page. It jumped to the second curve. We need to be down here on the third curve. So what I can do is hit the down arrow key. So sometimes when you have circles and you have to put it in as two curves, that gives you a total of 3 images on the screen. So you have to use the up and down arrow key to make sure you can get close to that intersection. And now I'm going to use the left arrow key, the right arrow key, and that gets me over there. And now I can hit enter. And this is a decimal again, but negative square root 2. So I did have to use the up and down arrow keys to change my curve here, change which section or which y equals it was on. So here there was 3 y equals. So the up and down arrow key, when you do the intersection, changes which intersection it's on. But we can still check and see that our answers are correct. So in both E and F, these are problems that you would probably have to do algebraically, but we do have that graphing calculator that we can fall back on to make sure that we're doing this correctly. Go ahead and take a look at G. If you have not done a circle one yet on your own, pause the video and do G, give G an attempt, and then we will come back and do both G and H together. Okay, so for G, hopefully you noticed that one of the equations was set equal to y. We need to set the other equation equal to y. So in the numerator, we do need to subtract x squared from both sides. So y squared equals 16 minus x squared. Now we do need to square root both sides to get rid of that x squared. So remember, when you square root in the process of solving, it comes with a plus or minus. So here are my two x equals. So here are my two equations. Y equals x minus 4, and y equals plus or minus the square root of 16 minus x squared. So x minus 4 equals plus or minus the square root of 16 minus x squared. I need to get rid of a square root. So in order to get rid of the square root, you square both sides. So now x squared, remember I need that middle term when I square here, so this would be minus 8x plus 16. If you want to distribute that, you always can. Equals 16 minus x squared. It's quadratic, so let's make it equal to 0. So I'm going to go ahead and add x squared to both sides, subtract 16 from both sides. So this gives me 2x squared minus 8x equals 8x equals 0. To factor here, a different method of factoring that we haven't done yet in this notes, but we see there's a GCF. Both of these are multiples of 2x. So I'm going to factor out a 2x. So 2x equals x minus 4. So basically dividing or taking a 2x away from both terms. And that's still equal to 0. Now I can set my two factors equal to 0. So 2x equals 0, and x minus 4 equals 0. So now, divide by 2 on the left. X equals 0 is one solution for x. Add by 4 on the right. So x equals 4 is my other solution for x. To find my y's, I can substitute back into either of the two equations. I'm going to choose this one, y equals x minus 4. So y equals 0 minus 4. If you need to do that in the calculator, you can, but y equals negative 4. So here's a coordinate pair that goes together. Substitute in here x equals 4, so x equals 4, y equals 4 minus 4, which is 0. So here are my two solutions. Now let's double check that on the calculator. So again, I have a line which I can just put in as x minus 4. And then I have a circle, so I need both the positive square root, so it's positive square root of 16 minus x squared, and the negative square root. So negative square root of 16 minus x squared. Take a look at the graph. And if we graph here, we can see one of the intersections here. The other one, it's kind of disappearing. It's not showing up to us, but we're going to be able to find that one as well. So let's go ahead and let's hit second trace intersect. And I'm going to do this one down here in the bottom left. So I'm going to move my cursor close to that bottom left intersection, hit enter. It moves my cursor up to the top curve. So remember, I have to push the down arrow key to move it down to the bottom curve and then hit enter. And now when I guess, I get the intersection. Now this is slightly rounding it here, but this is touching to the negative 14th power. So this is basically, it's giving us 0. It's just slightly rounding that. So 0, negative 4 is correct. Now, if I try to find the other one, second trace, I'm going to hit intersect. And then I'm going to scoot it over to where that second intersection should be. Hit enter for the second curve and hit enter. What's going to come up is, if we wait on it here, no sign change. So the problem here with the graphing calculator, some of these older graphing calculators, it doesn't pick up anything on the x-axis. So to account for that, if we know a solution's on the x-axis, and this one is on the x-axis, it's where y equals 0, we can see that in the table. So if I hit second table, let me get out of here, hit second table, and I go down to where x equals 4, it's going to show up as zeros on the calculator. And so x equals 0 does give me y equals 0. So even though you use the intersection key because of some programming things and some of the older calculators, when you use the intersection, it comes up as no sign change and doesn't exactly give you that answer. But if you look on the table, where x equals 4, y does equal 0. And so the table is a good way to also check your answers. So there we have our two solutions. Our two solutions, if we put them as coordinates, would be 0, negative 4, and 4, 0. Finally, the last problem is another circle and a line here. This one's written a little bit differently. This is the first time we see a horizontal translation with a circle. The line is already written in the correct format, so I'm going to put a little star by this because I'm going to come back and graph that eventually. The circle, the top equation, I'm going to go ahead and rewrite. So I'm going to write down the entire equations for this first step. Because what I need to do here is actually move the entire set of parentheses. Remember, you can subtract by a quantity. So I'm actually subtracting this entire quantity over to the other side. So this would be y squared equals 8 minus the quantity x plus 3 squared. Now, when I square root both sides, y is by itself, plus or minus the square root of 8, and then in parentheses minus, or sorry, and then minus in parentheses x plus 3 squared inside the square root. So it's similar to what we saw over here on the last example G, but with the x, there's a addition. Now I have two things set equal to y. Here's one, and there's that other one at the top. So we can set them equal to one another. X minus 3 equals plus or minus the square root of 8 minus x plus 3 quantity squared. To get rid of the square root, again, we do have to square both sides. Remember, the plus or minus basically goes with the square root. So on the left side, I'll write, the right side, I'll write that first. The square root is gone, but everything else is the same. So I still have 8 minus x plus 3 quantity squared. On the right, I have x minus 3 quantity squared, which if I want to square that out is x squared. Actually, I'll just write it down for now. Now, to simplify this, we do have to square out these two binomials. So x plus 3 and x minus 3 are not the same. They don't cancel or don't add or subtract or anything. So we need to square out those values or multiply out those values to simplify this. So if I square this binomial, you do have x squared, you do have 9. That middle term is taking these two, negative 3 and x, multiplying and doubling. So that would be negative 6x. On the other side, I would have 8 minus, I would have an x squared, I would have a positive 9. Then I would take 3 times x and double that, which would be 6x. It's quadratic. So again, with all quadratics, make it equal 0. So add x squared to both sides, subtract 6x from both sides, subtract 9 from both sides, and subtract 8 from both sides. So everything on the right is now subtracted to 0. On the left, I get 2x squared minus 12x minus 8. So the plus 9 minus 9 cancel out, and then leaves me with negative 8. I can try to factor this, but I could also notice that I can simplify here. I can divide both sides of the equation by 2. Everything divides by 2 here, so 2x squared divided by 2 is x squared. Negative 12x divided by 2 is negative 6x. Negative 8 divided by 2 is negative 4. So if you wanted to factor there, you could try, but it's easier here to simplify this equation. So if I tried to factor here, I'm looking for values that multiply together to give me negative 4, but add together to give me negative 6. You may realize that these values probably don't exist. So this is not easy to factor. Well, if it's not easy to factor, let's go the quadratic formula route. You could try to complete the square here. That would definitely be a valuable solution or viable solution. But if it's not easy to factor, let's make sure that there's actually some answers for this and use the quadratic formula. So negative b, remember a, b, c are the coefficients. Negative b is negative 6. So b is negative 6, so negative 6 would be positive 6, plus or minus the square root of negative 6 squared minus 4 times a, which is 1, times c, which is negative 4. All over 2 times a, which is 1. So now that gives me 6 plus or minus the square root of negative 4, sorry, negative 6 squared minus 4 times 1 times negative 4. We get the value 52 all over 2. Shoot, I made a mistake. Sorry about this, guys. I thought I was going to go a video without making a mistake, but sure enough, I did. So notice back here at the step where I distributed terms, there's a negative. Hopefully some of you guys caught this. But there's a negative in front of this x plus 3. So that's going to change all the signs. So when we do multiply out this x minus 3, let's go back to this step, multiplying out this x minus 3. We did this one correct. X squared minus 6x plus 9. When I multiply out the other one, it's a negative is distributed to everything. So this would be negative x squared minus 6x minus 9. I apologize for that, guys. Hopefully some of you guys caught that mistake, but we do need to make sure that we distribute this negative to everything as we multiply it through. So now we can follow the same process that we did. So it is still a quadratic equation. We still want to get this thing equal to 0. So add x squared to both sides. Add 6x this time. So now that gives me 2x squared. The 6x is gone. I can add 9 and then subtract 8. So this would give me 2x squared plus 10 equals 0. Now, it still does divide by 2. So x squared plus 5 equals 0. And this is a lot easier to solve. Subtract 5 from both sides. So x squared equals negative 5. And now, to get rid of the square root, there's the square, we have to square root both sides. So x equals plus or minus the square root of negative 5. And what do you notice here? There's a negative inside the square root. So we have no solution. So this specific equation or system of nonlinear equations does not have a solution, because when we solve this correctly, again, apologize for the mistake, it gives us a negative inside of the square root. So imaginary answers are not going to be answers on the graph. Let's double check this graphically. So y equals x minus 3 is our first graph that was given to us. The other, again, is a square root, so we need both positive and negative cases. So positive square root of 8 minus, and then in parentheses, make sure you put in parentheses x plus 3 quantity squared, and then close the parentheses for the square root. So you got to be careful when you type that in there. You do need that parentheses around x plus 3 before you hit the square key. And then we can graph. So if we take a look, there's our line, and there's our circle, and they do not intersect, so this has no solution. Okay, so this gives us algebraic. There's a lot of practice on algebraic solving. I'm not going to expect you to be able to solve all of these algebraically. Like a problem like number or letter B, that one is highly unlikely to show up that you're going to have to solve this algebraically. But I wanted plenty of practice in the algebraic solving method and then using a graphic method to check. We are going to see some word problems from time to time with systems of equations. Now, each of these word problems should be familiar to us, basically. We've seen these examples before, we just haven't called them systems of equations. So in problem number 3, it says Sally's high school is planning their spring musical. The revenue R generated can be determined by the function R of t equals negative 33t squared plus 360t, where t represents the price of a ticket. The production cost C of the musical is represented by the function C of t, which equals 700 plus 5t. Sketch a graph of the two functions, then find the highest ticket price that can be charged without losing money on the event. So we have an equation for revenue and we have an equation for cost. What we want to find is how can we use, or how can we set the ticket price so that we will not lose money. So the revenue here is going to be an equation that we're just going to go ahead. It's basically giving us this equation equal to y. So there's nothing that we have to rewrite here. We're going to go ahead and just enter this equation into the calculator. So I'm going to type in the equation as I see, negative 33x instead of t squared plus 360x. If I look at the cost function as well, it's basically y equals this expression. So I want to type that one in, 700 plus 5x. So we're going to have two functions on this graph. We're going to label the x-axis when we graph this. The x-axis is given to us. It's the t value technically, so that we can call it the t-axis. The t-axis is the ticket price. We don't have to put numbers on there yet, but T is going to stand for ticket price. The y-axis we're going to leave alone because it's going to be revenue for one and cost for the other. If you want to label this as revenue slash cost, you can, but you don't have to necessarily label this. We're actually going to label our graphs as we come through. So if I go ahead and I want to graph this, setting up the calculator is the important part here. So I'm going to set the window. Ticket price is not going to be less than 0. So I'm going to set the X minimum to 0. Hit the window key, set X minimum to 0 because their ticket price is not going to be less than 0. We don't know what the ticket price could max out at. Basically, we want to be able to find an intersection, at least one intersection between revenue and cost. We know that this is going to be an upside down parabola, so it's going to look something like this. We don't know exactly what it's going to be. We know that this is going to be a line. It's going to look something like that. We don't know exactly what it's going to be, but we need to be able to find the intersection. So let's make sure our x value is big enough to find the intersection. Let's set it to, I don't know, 50 for right now. I'm going to hit 50 for x max, and then it's zoom and go down to 0 to zoom fit. And then it's going to set my y values for me so my graph fits the x values. So what I see here is there's a little bit of a curve up there, but most of it is negative. So I set this way too big. Let me bring my window down. Let's set the X max to, let's bring that down to 10. And now hit zoom, fit. And this is better. So I've got a picture for my graph here. I'm going to go ahead and label this on the x-axis as from 0 to 10. Now, it doesn't matter if I show the entire curve because all I'm looking for is intersections here. So this is the two intersections. So the first curve was revenue. I'm going to draw this one in a different color. I'm going to do different colors. If you have different colors, great. If you don't, that's okay. But I'm going to go ahead and draw in the revenue curve. Looks something like this. And it doesn't go all the way back down to the ground. So this right here, I'm going to label this as revenue, or R of X. And then the curve, or not the curve, but the line for cost looks something like this. It's a little steep. Flatten that out a little bit. Something like that. Okay? I'm going to label this C of T, not X, but C of T and R of T. So there are two intersections here, and it's a system of equations, so the intersections are the solutions. Now the question was, sketch a graph of the two functions and then find the highest ticket price that can be charged without losing money. So revenue is the money that we're bringing in. This blue curve represents money we're bringing in. C is the red curve, or the red line here is cost. So as long as the blue curve is above the red line, we're making money. Once they intersect, that's the part where we're breaking even. So it says, again, find the highest ticket price. So we want the furthest amount to the right that we can go that can be charged without losing money on the event. So basically what we're looking here for is this intersection. The intersection to the right. There's two intersections, but we want the highest ticket price, so the intersection to the right. So to find that, hit second, trace, intersect, and move to the right. I'm going to go ahead and move my cursor over there until it gets closer to that right intersection. There it is. Hit enter. It stays close to that right intersection, so I'm going to hit enter. You don't need to guess. And there we have the point. So remember, T is ticket price. The X value is ticket price. So I'm going to go ahead and round this to two decimals. Now, the important thing here is to understand where we're rounding. If I round this number up, I'm moving slightly to the right of that intersection, so I'm actually losing money. So I need to make sure I round this number down
to the nearest cent, 8.15. And then y would be 740 point, if we're moving this rounding to the left, rounding to the left would be slightly over here. So 740.79. That number, the y value would round up. So we do need to round the money down, because if we round the money up, we move past this intersection, and now we're not making enough. We're losing money. So what is the highest ticket price that can be charged without losing money on the event? Approximately $8.15. Now, if this was a real problem, we would want to maximize revenue in comparison to cost. We'd want to maximize profit. And so what we would do is we'd compare these two, the value or the distance in between these two curves, and then find the ticket price that way. But in this instance, we just wanted to see where can we go to make sure we don't lose money. So this would be that intersection on the right. So if it doesn't tell you that you have to solve algebraically, let's go ahead and let's do a graph, and let's use a graph to solve. Let's take a look at 4. In problem number 4, it says a pelican flying in the air over water drops a crab from a height of 30 feet. The distance the crab is from the water as it falls can be represented by the function h of t, where t is time in seconds. To catch the crab as it falls, a gull flies along a path represented by the function g of t. Can the gull catch the crab before the crab hits the water? Sketch a graph to support your answer. So here again, we want to draw out a graph. We know that the x value here, the x-axis, we're going to label that is t. It's time. So both of these are in respect to t. So time is the x-axis. So I'm going to go ahead and write this as time, and this is in seconds. Now, even though these are two different equations, the y-axis in both is height, and that's in feet. So the goal is flying along this path that's represented as the feet of the goal above the water in seconds, after whatever seconds. So the water is basically our x-axis. When the crab hits the water, the goal can no longer get it. We need to see if they're going to intersect before it hits the water. So we can do this graphically again. It tells us to sketch a graph, and that's probably the quicker way to go here. So take negative 16x squared plus 30, and take negative 8x plus 15. Again, we know that the x minimum, I'm going to hit the window key and set up my x minimum and x maximum. So where x is time in seconds, 0 is going to be the least amount of time, so 0 under x minimum. For right now, let's just let x max be 10, and let's see what happens. Let's see what kind of picture we hit. Zoom and go down to fit. And that's actually a little bit too much. Most of this is just negative. So let me go ahead and reset that window. Let's cut this down to, let's say 4. Zoom, and then actually let's make this 3. And then window, sorry, zoom and fit. So my X max, I went ahead and made it 3, and then fit. And there we see a path. You could cut this down even more if we wanted to. You could draw the graph that you saw, or I'm going to cut it down just a little bit more and make it 2. And here's my curve. So I'm not going to draw the negative portion of the curve because we're not too concerned about that. But again, I'm going to use different colors. So h of t is the height of the crab, and that's represented by the parabolic curve. So there's my height of the crab, and it doesn't have to be perfect, but we want something that looks kind of like the graph we see. And here's the goal. The goal is flying at a rapid pace to try to intersect that crab, or a steep angle. And the question just asks, can the goal catch the crab before the crab hits the water? So the height of the goal is represented by g of t, and the height of the crab is represented by h of t. So we don't know for sure if the goal is on path to catch the crab, but we do know that the height is appropriate, that it's going to intersect at this location going to intersect the height of the crab before it hits the water. So we could say it didn't ask us at what time or at what height. It just says can it intersect, and we could say yes. And if we wanted some reasoning, we would say that the goal, or g of t, equals h of t. The height of the goal is equal to the height of the crab before, um, sorry, let's say where h of t is less than 0. So it's going to happen before the crab hits the water, which would be 0. Sorry, h of t is greater than 0. So it didn't really ask for reasoning. You could just say yes and point to that intersection on the graph, but there's some reasoning there behind that. So again, we're setting up graphs to help us solve these systems of equations here, not looking for a solution, just if a solution exists. Finally, problem number 5, the last one. The price of stock A of x over a 12-month period decreased and then increased according to the equation A of x, where x equals the number of months. The price of another stock B of x increased according to the equation B of x over the same 12-month period. Sketch a graph of both equations. State all prices when both stock values were the same. When did this happen? So we want a graph. We want to label the x-axis. The x-axis, they're both going to have the same dependent variable. That's going to be true for all systems that we evaluate. That's what makes them a system. They have the same dependent variable. So the stock price for A of x and B of x is in relationship to x that equals the number of months. So this is the x-axis and this is months. And it does say over a 12-month period. So this tells us how long we're looking for on the x-axis. We're looking from 0 to 12. We want to sketch a graph to represent this. Again, here there's no work really to be done. They give us the two equations. So all we have to do is go ahead and input those two equations into our calculator. So 0.75x squared minus 6x plus 20 and 2.75x plus 1.50 or 1.5. And then I'm going to set my window. This time I know exactly what to set my window to. The x minimum is 0. The x maximum is the months, 12. Then I'm going to hit zoom. I'm going to fit it. And now I can sketch my curves. Now, my window right here is not showing all the way down to the y-axis, so I'm actually going to bring this down to the y-axis. I'm going to set my y minimum to 0. You don't have to, but I always draw the y-axis, sorry, the x-axis. I always draw the x-axis in my picture, so I'm always going to include the x-axis on my window here so that I can see that. So here, let's go ahead and sketch these in. So A of x is the quadratic here. So it looks something like this. Oh, that's really bad. Let's try that again. Something like worse. Might be better. Something like that. Again, it doesn't have to be perfect. Just look something like the picture that you're seeing. And sorry, let me label that. This is the stock that is A of x. And then the line B of x represented here. Now I'm going to go ahead and label the y-axis because both the y-axes are relating to the same thing. Both of these are price. And this is in dollars. So the price of A of x and the price of B of x. In order to find the prices when both stock values were the same, we want to find the intersection points. So let's find those intersection points here. So second trace intersect. I'm going to move over here to the one in the left first. So go ahead and just move that over to the left, hit enter, hit enter, hit enter, make sure my cursor is close here. Now in this one, rounding is not necessarily dependent on the question. It just tells you what the price is. So we want to round, for the price, we want to make sure we round to the nearest 2 decimals because it is dollars. For month, I'm going to go ahead and do the same and just round to the nearest 2 decimals. So 2.77 and 9.13 for the first stock. or for the first intersection. And then for the second intersection, second trace intersect. Again, now I need to move my cursor all the way over to the other intersection. Sometimes a little bit tedious, but these are numbers you're not going to find on the table because they are decimal approximations. So we do need to use this feature. Once we move it over to the right, or close to that second intersection, we can find that intersection point, and that's about 8.89, 25.96. So it says state all price values. State the all prices where both stock values are the same. And so we see over here on the left, the value is $9.13. So one time that they're the same is $9.13. And this also asks when did this happen? So this would be during or towards the end of the second month. So the first time that they're the same is $9.13, and that's towards the end of the second month, so 2.77. And then it's $2. Sorry, again, they intersect over here. The price would be the Y value. We have that labeled on the axis, $25.96 towards the end of the third month. Sorry, not the third month, of the 8th month. So the x-axis is our month there. We have that labeled. Sorry, I'm struggling to write and talk at the same time. So the x-axis is the month, so it's towards the end of the 8th month, almost at the 9th month. If you wanted to break that down by day, you could, potentially, but this is good enough rounding for our purposes. So when we have word problems, unless we're told that we have to solve these algebraically, we want to go ahead and set up graphs. Use those graphs, making sure we label the x-axis, the y-axis, we label our functions, we label our intersections when we need those for the answers. So like in 5, we needed the numbers for the answers. In 4, we didn't need the numbers for the answers, so we didn't find that point necessarily need to. In 3, we did label that point because we needed that number for the answer. So if you need the number from the answer, label that point and then give your answer in context. So if it doesn't tell you to solve algebraically, we can definitely do this graphically and find those graphic intersections. If it does tell you to do this algebraically, we have many examples of how to solve algebraically. Again, basically what we're finding there is intersections on a graph. So the possible solutions occur where the one function intersects the other function. And with this, we have covered all of SE.3. So this was a little bit of a longer section in terms of notes because of the work that it takes algebraically. When it comes to your guys' assessment, you're not going to have to do as many algebraic problems as you're going to do graphic problems, because graphic problems are a lot faster for us to be able to solve using our technologies. And it's good to know how to use those technologies. That's something that's going to be available to you when you get to the workplace. At this point, if you have taken good detailed notes, make sure you guys keep track of those notes for the SE3 online assessment that will come at the end of the week. There will be homework posted. If that's posted already, you can find that on the Google Classroom classwork tab. For school level guys, that's going to be on the IXL. For my honors guys, that's going to be the worksheet posted there. Make sure that you guys are working on the posted homework and you pay attention to the Google Classroom Stream tab. I will have an update on the next time that we will have a Zoom session where you guys can log in, get questions answered, and help before we have that online assessment. Thank you guys for tuning in for SE3 Notes, Nonlinear Systems of Equations.